Cool. So I just want to give everybody sort of, use the mic. Can you hear me?
Not great.
Can I? Okay. All right.
Our mic was not working earlier, so maybe.
Okay.
It's working good. Okay, great.
So yeah. So first, I just want to give everybody sort of an idea about how I kind of want the discussion to go. So we're going to start out where what I'm going to do is just, in case you didn't have a chance to read the paper or you're confused about things, I'm going to sort of give a summary of the things I think that are the most interesting parts of the paper, just so that everybody can kind of be on the same page. And then we'll have a little bit of time to talk about things that you want. But then we're going to try something new where I've pre-appointed some people to be discussion leaders, and if you feel like you want to be a discussion leader too, then you can just raise your hand at that point in time. And we'll break off into smaller groups to try maybe, in groups of like 5 to 10 people, just talking about it, so that you can have a chance to ask questions. But maybe if you're nervous about talking in front of the whole group, you don't have to be nervous. It's only 10 people, whatever. So we'll give that a shot. So with that in mind, this paper is about Sparrow. So Sparrow is the thing I think that really captures Sparrow best is, or at least the thing that they wrote that captures Sparrow best is that it's a decentralized, randomized sampling approach for scheduling that provides near optimal performance and scalability. Now, something that I kind of want to plant the seed of in your mind is that although this paper talks about Sparrow in reference to things like compared to Hadoop or compared to Spark, I also think that Sparrow is really something that we've all probably dealt with load balancers at some point. And that Sparrow really kind of looks like a load balancer if you sort of tilt your head a little bit. And so I kind of want to just plant that seed while we start talking about some of the techniques that they use, because I think that that's actually a really interesting thing in this paper. So what is Sparrow? Well, the idea is that what we had was we have these frameworks like Hadoop, and what Hadoop does is it improves this thing that we used to do before. Let me do this on my harder. So what we used to do was we had some computers. And what we would do is we have some problem. So like here's our problem. And we make our problem into some data. And then we would send that over to the computer. And that's what we did 15 years ago, 10 years ago. Then Hadoop came out, and we changed this around. Do you guys know that marker or an eraser?
Oh, you can use the towel. Yeah.
So what we did then was we changed this so that instead of sending our compute to the data, instead of sending the data to the compute, we would send our programs to the data. So now, but what does it mean to send a program? In this case, our program is some kind of binary application. Now, what was the win here? Well, our problem data, it kept getting bigger and bigger. Maybe, over here we got like 10 gigabytes of data. And our applications, even when our applications are really big, they're not that big. Maybe, I don't know, say 100 megabytes for a really big application. So it was more efficient to send our program over to the data. But Sparrow changes that again. And what we do in Sparrow is we send our data to the compute to the data. And so what I mean by that is, so we have our problem. Okay, it's like 10 gigs or whatever. And in the Sparrow paper, they mention things like Yarn and Slurm and Mesos. And if you know what I'm talking about and you read the paper, and you're like, cool, this will make sense. You didn't read it, doesn't really matter. There's these things, they don't matter. So what we do is we take these programs and we send them over to the data. But the problem still is this program's 100 megabytes. Now, uploading a 100 megabyte file, it takes like a second or two. But one of the motivations of Spark is what they want to do is they want to make it so that you can just log onto a website and get real-time interactive queries where you can, maybe like you jump to your email and you don't just see your email, but it searches every email that everybody in your company has ever sent. But not just your company, everything in some multinational conglomerate. And it doesn't just filter all those emails, but it also applies like privacy rules to them so you can't see secret stuff. So we want to do lots of computation. And the problem is that all those rules, they start to get pretty big to encode if we want to send over the application itself. So with Sparrow, what we're trying to do is we're saying, well, really, the data is just like the string, email. And then what we're going to do is we're going to send this string over to the program, which is bigger. And the program is, hopefully, we already sent it over to the data. And so what we end up doing is we end up sort of being able to send in even smaller amounts of data in transit, which helps us, it's one of the ways that we can improve performance. So that is sort of the design goal. So then, can I get this chair? I don't know if you have another chair.
Oh, yeah.
Move closer to me. Cool. So basically, this is the idea. Now, I want to draw another parallel here. So, does everybody knows how HTTP works? Or like making a web request? Even if you didn't know that was HTTP, that's over HTTP. So really, in that case, we're doing just that. You, in your HTTP request, send your little request, that's data. It goes over to a web server, that's some compute. And that web server lives in the data center near some databases. That's your big problem data. So really, in some sense, what we're doing is Sparrow is taking inspiration from this web application architecture where our clients are sending requests to our servers, and our servers make up responses and send them back. Now, there's a few things, though, that Sparrow does differently. Differently than it is than a regular load balancer or than a regular sort of web app. And there's three things, I think, that are most interesting. So those three things are, one second. All right, so those three things are power of two scheduling, batch sampling, and empirical measurements. So let's go over each of these things in turn. So one thing I think that that the Sparrow paper, it just doesn't explain it all, is this power of two sampling. There's a little bit about it, but it's a really interesting idea, and I think that it's also something that even without understanding much about statistics, it's something that we can all get. So this is the one thing that if you get nothing else out of the paper, and if you get nothing else to explain to you, this thing I want to make sure that everybody has some idea how it works. Speak more to the mic. Can you guys not hear me in the back?
Nope. The mic's off.
Okay.
Oh, that's right.
I'll talk. I'm just gonna. Can you just hear me if I talk like this?
Yeah.
Okay, great. I'll just talk like this.
Wow.
So right. So what's the idea here? So normally, let's look at like we have this thing called request latencies, right? What that means is sometimes when I make a request to some system, it takes 10 milliseconds, sometimes it takes 100 milliseconds. And what we can do is we can actually visualize that. So what we can do is we can make an axis where this axis is the latency. And generally, if we look at it, it looks something like this. So over here, these are low latencies. Over here, these are high latencies. Does this chart make sense to people? Okay. So now, the goal is we want to do two things. One thing is, instead of it looking like this red chart, say red is bad, we want it to look more like this green chart, which is good. And what this means is we're not seeing, some really fast, some really slow. We're trying to sort of make them all be about the same speed. The other thing that we want to happen is we just want to shift this as far to the left as possible. So those are the two goals. And so power of two scheduling is how we're going to do that. So the idea here is, well, what if we could guess, or what if we knew in advance and we said, well, some machines we know they're over here on the right side, and some machines we know they're over here on the left side. All right, and so what we're going to do is we're going to say, well, if we always pick machines on the left side, then we're always going to be doing better than the middle. Now that doesn't exactly make sense, because if you're always doing better than the middle, well, that doesn't, where the middle moves as you continue to beat it. So at some point, you can't do better, and you just get to as best as it can be. And so that's this power of 2 scheduling idea. So let's see what that looks like. So the idea is, what happens if we pick random servers? Well, random servers, we could be anywhere here, and that's what this chart represents. But if we do power of 2, what we're going to get is this, a little chart, little square. So this side is one request, and this side is the other request. Because remember, we're checking 2 servers to see which one is going to actually serve up our request. Now each of these servers, there's 2 types here. There's going to be 2 fast servers, and there's going to be 2 slow servers. So each of these squares happens with 25% of the time. 25% of the time, this request is going to get a server that is faster than half of the others. 50% of the time, this request is faster than half. 25% of the time, this one is slower than half. So what does this mean when we look at this chart? Well, it means that in 3 out of the 4 cases, we actually end up with a faster request than the median. In only 1 out of the 4 cases, we end up with a slower request. So I think this is a nicer sort of intuitive model for why the power of 2 scheduler does so much better. Now, we can actually see how much better it does by a chart that they have. Let me find that chart. So if you have the paper, it's on page 4. If you don't have the paper, I'm just going to sketch it really quick. So I've tried to color match the chart in the paper. So what we have here is we have 4 little things where this axis is the response time in milliseconds. And this other axis is the load. The load, that sort of represents the difficulty factor. So generally, obviously, if you only ever get 1 request at a time to your system, it's always going to do great. Things get harder when there's more things going on. So basically, but I would consider this sort of the difficulty of the problem we're trying to solve. So what we see is that in the red case, that's where we just pick a random server. And we can see that as requests increase, the latency increases. Now with the blue one, though, that's where we start adding this power of 2 sampling. And you can see that actually, for a while, it does pretty well, and it only starts to perform poorly the further we go on. Now, the green one, what the green one does is something called batch sampling, which is the second point in this paper that I think is pretty interesting. So before I go into batch sampling, though, I want to ask, does anybody have any questions about the power of 2 stuff or sort of the motivating factors of this paper?
It's not clear why they call it power of 2.
They call it power of 2 because
I think it's originally power of 2 choices.
Power of 2 choices? Okay.
Power, you gain power by having 2 choices.
The original power of 2 choices was popularized by Michael Witzenmacher in some of his work after grad school, where basically it's for a generalized probabilistic model of load balancing, you actually have a much tighter bound on the expected max load of any bin if you're randomly allocating balls to bins, if you pick the min of 2 random choices. If you want to learn about the power of 2 choices, you should read the papers by Michael Witzenmacher. They're very good.
Right, so that's another way to think about it, or the way that I like to think about it, and this is something that as we sort of go through batch sampling that you'll see, is that in this case, essentially what we're doing is we're picking, when we say we pick 2 servers, you see 75% of the time we do better. But what if we instead, for each one of these, we chose 4 servers? Well, then we'd have this like 16 element matrix. And if you go through the 16 element matrix and see how often say instead you look at the fastest quarter server now, and then you look at the 16 element matrix, and you'll see that actually, a bigger chunk of the 16 element matrix will be in this, we're doing better than the median camp. So, it's also there in that it's, the power is a knob that you can turn. And we'll see how you can turn that with batch sampling better. Yeah.
This assumes all the servers are equal in their ability to serve.
It does. Now, the last thing that we look at, the empirical measurement, that is going to compensate for the fact that, that our idealized model of all servers are equal isn't true. And instead, we're going to say, how are servers doing right at this moment? And we're going to schedule based on that information instead. Cool. So, batch sampling. Batch sampling is another thing that I think is it's really cool. Trying to figure out how to get the ink off the board. So for batch sampling, the paper I think has a really great example. So I'm just gonna reiterate the paper's example for why batch sampling works. So let's look at two example probes. Now there's two types of servers. We're gonna call them fast servers and slow servers. Okay. So we have request 1, and request 1, it's going to get 2 slow servers. And then we also have request 2, and request 2 is going to get 2 fast servers. So what this means now is that request 1, its response time is going to be slower than median, but request 2, its response time is going to be faster than median. What batch sampling says is it says, hey, why don't we just do this all as a batch? So we'll probe 4 servers for both requests simultaneously, and then we'll take the best servers out of all of those probes, and we'll use those together. And when we do this, then we see that actually both requests will get a fast server, where had we probed them separately, they would not have both got fast servers. And this just generalizes. So the higher the throughput that you get, the more probes you can do simultaneously, and then the more there exists different sort of shufflings where, oh, this one had a really good luck probe and this one had a really bad luck probe, so we'll just kind of share that information among them so we get a better result overall. So that's this batch sampling idea. And this is something also that, I think I really want to, the thing that I like about this paper so much is that they're taking these ideas that are really popular in in web architectures and in improving performance of databases and improving performance really of everything. And they're just applying it to this different domain. So, we saw this power of 2 scheduling, which came from load balancing. Now we're seeing this batch sampling, which is really, we're just saying, let's just batch all the requests and try to, get some better work done here. This is something where if you ever used MongoDB even, I don't know if they still do this by default, but for a while there was a lot of people who did not like MongoDB because it would try to batch up the writes as it made them. What that meant was that if you killed MongoDB at the wrong time, you'd lose all the writes in the batch that hadn't been written yet. But this is a trick that that's pretty popular to use, and it's something that you can take away and sort of see that works in really small things that don't work well, works in really big systems that are fast. So that's batch sampling. Does anybody have any questions about batch sampling? Yeah.
When the requests are hitting the server, how are they deciding which one is best? Do they have to go back and tell where they were sent from, or how does that decision made?
So what happens is, so let me draw another chart to explain this. So what we do is we have these, I'll move out of the way in a second. We have these things, these sparrows, okay? And then we have some workers. And each of the workers has a queue. So what happens is a user connects to one of the Sparrow schedulers, and then the Sparrow scheduler randomly picks some workers. In this case, we're doing the power of 2 picking, right? And so what it does is going to connect to pick those workers that it picked and say, hey, workers, how many elements are in your queue? And we're going to say the number of elements in a worker's queue represents how fast that worker is. Because sort of intuitively, the more work it has, the longer the queue, the longer it's going to take for it to answer. And conversely, the shorter the queue, the faster it's going to answer. So does that answer your question?
I think so, yeah.
Cool. Did you have a question?
So I just want to make sure that request 1 and request 2 are 2 different requests that the same person is making. And instead of sending off each request independently, you're sending them together, and you're sending it to all 4 servers instead of each request individually sending to 2 servers.
Right. So the idea is that these requests are coming into the Sparrow schedulers. Okay. Now the Sparrow schedulers, though, they need to make these probes, which I represented by these arrows.
Okay.
And so these are the probe results. So what we're saying is, well, if one Sparrow scheduler if for each request it probes them independently and does not share information between those probes, then it's not going to do as well as if instead every 50 milliseconds it batches up all of the probes, all of the requests that it's gotten, does all of those probes simultaneously, and then looks at the best results of those.
Okay. Just double checking on that.
Yeah. Right. It's basically the idea is that when you treat them all independently, you get this, you get the one result, which is sort of the power of 2 improvement. But when you do the batch result, you have these other cases like where one of them is especially bad or one of them is especially good, and then that additional shared information results in it, gives you a better result.
Okay.
Or in the back.
Is there an optimal size for the batch size? Like, it would make sense for you to wait until the batch is the size of all your workers, right?
Right. So the idea with the batching is really it ends up being sort of a latency performance trade-off, where the longer you wait, the bigger your batch, the bigger the batch, the better the results. But the whole point of batching is to reduce latency. So you don't want to wait too long because then you're defeating the purpose of the operation. So generally, when it comes to batching, the paper actually explains 2 different batching techniques. One of them is that, so first of all, remember, Sparrow is really targeted at these MapReduce computations. So when you're doing a MapReduce job, the thing that comes into Sparrow results in Sparrow knowing it needs to execute 1,000 tasks, say, which means it can just immediately make 2,000 probes with 0, it doesn't wait at all, it just knows instantly that's what it needs to do. There is, it goes into more detail about placement constraints, and there's some problems with this type of batching with placement constraints, and for that, based on my reading of the paper, it seems like it waits every 10 milliseconds, it takes everything that's happened over that 10 millisecond period and batches that together. Is there a question over here?
Yeah. So each of those Sparrow nodes is making a couple of requests, but they're separate. They're separate machines. So there's added overhead then, and for them to coordinate their results to find the best results for each, across the batch, as opposed to each individual Sparrow node's answer.
So it's a great question. So the idea with Sparrow is that an individual Sparrow node coordinates an individual user intention. So if the user intends for something that results in 1,000 tasks getting executed, then that one Sparrow node is going to manage all of those tasks. One of the powerful features of Sparrow is that it's a share nothing architecture. This is something that most web applications try to do. They try to move all their state into the database, and in this case, our database is the queues on the workers. So instead of these Sparrow nodes needing to communicate between each other to coordinate something or to load balance, and to somehow meet their goals by communicating, instead they communicate when they talk to a worker and discover how long the queue is on that worker. That the queue length is sort of the data storage for the information of interest to Sparrow.
And the batching is done at that point, outside.
The batching is done inside of the Sparrow node. The workers are really dumb. The only thing a worker can do is say it can execute a task, or it can accept a task to be in queued and give you a response later, and it can also tell you how much is in the queue. That's all that workers need to do. For now, they'll do something new in a few minutes. Any more on batching? Cool. So now the next thing, the last thing that I think is really important in the Sparrow paper is this idea of empirical measurement. And I believe they call this late binding. So And it is, and they call, not only do they call it late binding, but it really is late binding. It's late binding in the sense of, you know, Clojure has some late binding features. Some other, I think Erlang has some late binding features in it. There's a lot of languages that have a lot of things, and they all call them late binding, and they are all late binding. Sparrow is another instance of this sort of pattern. So, so there's a problem with everything that I said here. It's a really big problem, and it turns out in practice that when you look at it, these ideas are good, but they're not great. They don't really make Sparrow into an awesome scheduler. They make it into a substantial improvement over the state of the art, but not like killer. And so this late binding thing, that's what makes Sparrow killer. So what's the idea here? Well, these Sparrow nodes and the way that it decides fast or slow, that's all based on queue length, right? We look at some things and we say, oh, this queue is 10 elements long, this one's 3 elements long. The 3 element long one must be faster than the 10 element long one. But that might not be true. What if the 10 element queues jobs all take 10 milliseconds and the 3 element queues jobs each take 1,000 milliseconds? Then the 10 element queue is 6 times faster. So it would be a really bad idea if we went on queue depth alone. So instead what we're going to do is we're going to measure and we're going to see which queue is actually faster. Now at this point you might be saying, okay, but that's pretty weird, because what you're saying you ask a question now about a thing that's going to happen in the future. Because right now I want to find out, whenever they're done, who is finished first, or who will be finished first. But we're asking that without having any information about what was happening. So how do we do that? The way we do it is that we're going to take this communication model and make it a little bit more complicated. So I'm going to make another diagram for that. So we have our Sparrow node here. And we have our worker over here. Now there's going to be a four-way handshake that these two are going to do. The first thing Sparrow is going to do is it's going to say reservation. It means make me a reservation on this worker. And so at this point, what the worker does is it puts a little thing into a queue saying, all right, I got you, you're right here. You're like 5th in line now. And so when Sparrow does a probe, the probes, they don't actually measure the queue depth anymore. Now our probe is it's like making a little ticket, like when you go to the deli counter or the bakery counter and you take one of those tickets. That's what we're going to do now. And so what happens is at some point, the worker's going to say, great, it's your turn. Are you still interested in this? Because I mean, I'm sure we've all went to the deli or any of those things, the ticket things, and got really pissed off that it took so long and just stormed out, kept our ticket. Because like nobody else can have this ticket. I waited all that time to get any food, so they can't either. And that's okay, that happens in Sparrow too. So the deli worker is going to say to the Sparrow, hey, do you want to run your job now? Because it's your turn if you're interested. At that point, the worker can say, yeah, sure. Here's my job. And we're going to pass that job on over. And at this point now, the worker actually is going to run the job for real. And then finally, in the final stage, we're going to send the results back. Now, what this does compared to the queue depth probe is that what we're doing is by putting in the reservation, the time that we get the first OK, that is the fastest one of whichever ones we probed. We don't care which ones we probed, but when we get that OK back, we know that one is ready. Because actually the node is idle. It's not actually computing anything when it says OK. And then when we run the job, it gets immediately run with 0 latency. Now, you might say, well, this is great. We've eliminated all the uncertainties due to queue depths being a poor approximation of the actual queue amount of work that's pending on that node. What's the penalty? Well, the penalty here is in this little region, and I'm scribbling in red. See, between the time that the worker says OK and the job gets back to the worker can't do anything because it's waiting for somebody to tell it what to do next. So what ends up happening here is that this late binding thing, it's more effective as the network latencies become short or the job lengths become long. So longer jobs and faster networks, this is a good idea. If your jobs and your networks are equal length, then this reservation idea doesn't work because you end up sitting idle for an entire job's worth of work and your throughput just goes through the floor or hits the floor and then sort of stays there. Now, there is another, there's another really interesting thing in this paper, or actually, so, all right. So this is this empirical measurement thing. Does anybody have any questions about this empirical measurement? Yeah.
Doesn't this then also mean basically a queue on the Sparrow worker too, of like the jobs that are waiting to be done, as opposed to queues waiting on the workers? Like you've moved the queue basically at this point.
So there's always sort of the set of pending tasks on the Sparrow worker because it needs to know what's still outstanding,
yeah.
Right? I would call it less of a queue. Well, okay, yeah, there is a queue also on the Sparrow worker. So the Sparrow worker knows what needs to be done. It makes all the reservations in a big batch. And then as it gets OKs, it starts shifting its queue from here to here. So yeah, we shuffled the queues around a little bit.
I'm just thinking of reliability. Like if you lose a worker, you lose 4 jobs in the batch sampling. But if you lose a Sparrow node, then you've lost a lot more jobs in this setup.
So actually,
am I wrong?
So you are, but not for the reason you think. So in both cases, you lose all the jobs. The idea with Sparrow is that the scheduler is stateless. The idea is that there's some client saying, I want you to run this job. And if the Sparrow node dies before the client gets its result, it just submits it to a different Sparrow.
Okay.
So that's sort of the underlying assumption throughout the paper. So yeah, so you don't lose anything more. If you tried to shift the persistence over here, then actually you're starting to move away from the shared nothing architecture, and there's all kinds of new distributed problems you get to deal with.
Right, yeah. So the client, the final source of truth of like what needs to be done still.
Exactly.
Okay.
So yeah.
So
Yeah.
does the Sparrow only reserve the task on one worker or multiple workers?
So these reservations, these are replacing those probes, either those power of 2 probes or the batch probes. So what happens is Sparrow gets some job. That job is 1,000 tasks. Then this Sparrow node, now that it has those 1,000 tasks, it's going to make 2,000 reservations. The first 1,000 reservations that it gets an OK for, those are going to run the jobs. The second 1,000, we're just going to ignore them because we're not interested anymore. Yeah.
I think they actually.
Oh, sure.
Okay.
Yes.
Was there some consideration in the paper? I don't know. I didn't read it. To say, well, why do a reservation? Why not just send the job? But then, when the worker's ready, it says, hey, I'm actually running it, and that could be sort of the protocol. Was that?
So I don't think that they talked about that.
Yeah.
I mean, one of the reasons. I mean, yeah, I think that would definitely improve for certain types of workloads. If we go back to that idea about like how much data are we transmitting, it may be that a job is a little bit bigger. I think generally the idea is that a probe is like we're on the order of bytes. A job is kilobytes. So it's 1,000x more communication throughput is required to send the job as part of the reservation. But for certain workloads, you could definitely do that. I think it was.
So if the worker is just coming back to the Sparrow scheduler every time that it needs a new job and you're sending the job at the time that it requests it, how is this particularly different than just a FIFO queue on the Sparrow side and a producer-consumer, like a classic producer-consumer scheduler? Doesn't it just kind of eliminate the entire batch sample empirical measurement model?
So you mean with the idea about why does the worker call back?
So like the Sparrow makes a call out to multiple workers and it's effectively saying, I enqueue all of you for the next thing that I have to run. And then the workers all come back and say, I have a thing, I have a slot to run on. And the Sparrow scheduler just hands back to him. How is this different than just that step? How does power of 2 batch sample and even the statement of, this is late binding, but how does everything else factor in that makes it fundamentally different from just the workers requesting work?
Yes, so I think that, so basically, I'm going to try to summarize it into a one phrase and see if you agree. So what you're saying is if we just had one big shared queue that all the workers are reading from, how is this different than that?
Well, I mean, you're sharding across Sparrows, but
right.
other
But even
than that,
in each Sparrow, why is each Sparrow not just one big shared queue?
Yeah.
Right. So if each sparrow was one big shared queue, then that means that each worker needs to know about every sparrow.
I mean, does it? Because effectively, it has been like you're setting up a queue of reservations across sparrows. You're saying like,
right.
I go back to this sparrow this time and this sparrow this time. You could easily flip it around and say this worker approaches random sparrows whenever it has worker ready.
So that's a great point. And so you may have heard of something called work stealing. And yeah, there's a really interesting, going back to the first PapersWeLove, I missed the second one, so I don't know if duality came up there too. But there is sort of a duality between this Sparrow model and work stealing, where in work stealing, our workers are pulling data, and here we are pushing workers to pull data. So maybe it's a duality, maybe it's really just sort of a subset relation. But yeah, those are very similar ideas. Yeah.
My question was just if the worker says, okay, I'm ready, and the Sparrow is no longer interested, does it actively have to send a message to say I'm not interested, or does the worker just time out?
I'll get back to that.
Yeah, how about prioritizing the jobs?
I'll also get back to that. All right. Yes?
So you have 2 Sparrow nodes, and they all probe random sample of the workers, but if you're a client and you want to run something on some workers, just because you ask that one Sparrow node to run your job, it doesn't mean that his workers, the workers that he probed, are going to have free slots. Like you might, if you had pinged a different Sparrow, then you might have had a free slot faster than if you waited for that one node. And so I'm not really sure how they deal with that, and also how they deal with like overcapacity. So one worker goes back to you and says, I have 1 slot, but you need 10 to run.
Right.
How do we deal with that?
So, all right, so let me answer the second one first. So, each job, the idea with Sparrow is, or actually I'll answer for both of those at the same time. The idea with Sparrow is that we're using randomized algorithms instead of trying to come up with a solution that solves the actual optimal problem. We're going to use a randomized algorithm that approaches the optimal solution. And the reason that we use the randomized algorithm that approaches the optimal solution, rather than doing everything, is that you can get much higher scheduling throughput. Some of the examples they gave was, so they talk about a system called Spark. Spark is the sort of in-memory MapReduce that's become very popular for like analytics stuff, because you can get an answer to your, a Hadoop job that took 10 minutes on Spark, it takes maybe 1 or 2 seconds. And so Sparrow was designed by the same lab that Spark came out of, and they're like, okay, well, what do we do for the next step? What if Spark wasn't just for research or for like analytics people, but it was actually for every single request was a Spark job? And so the idea there is, well, if you just look at the number of scheduling decisions you need to make per second, each node, you would need to make millions to hundreds of millions of scheduling decisions per second. If you consider like, a really beefy server, like, how big of a server do you get for like 10 grand? You get maybe like 40 or 50 CPUs, a couple hundred gigs of RAM. Like you'd think this is really fast, but that machine is going to get to make 10,000 decisions per second, maybe 100,000 scheduling decisions per second. And so in order to achieve that level of scalability where you can actually solve an infinite number of these per second, I mean by continuing to throw more machines, and also with the caveat that at some point nothing works. But to do a lot better, you need to start splitting this stuff between the multiple sparrows. You need to trust that the randomized algorithm in expectation works well, and generally, and basically the idea is randomized stuff, it works pretty well. The power of 2 thing really helps control the tail latencies. The late binding helps deal with the fact that we can't estimate queue depths accurately. And so, when you look at it in practice, it actually works really well. Now, coming back to the capacity problem, so that's actually a really interesting question. So, what happens if your cluster can serve, 1 billion requests and you get 1.5 billion requests? Like, what do you do? Well, you fall over. That's the only answer to that question. And that's something, you see this in most companies that start getting really big data centers with like hundreds to thousands to tens of thousands of machines. What they do is they do capacity planning and they ensure that they have more capacity available for serving than they do for the requests. And when they do start hitting that capacity limit, they start rejecting requests. And you can see even in the Sparrow paper that when they hit around 80 to 90% load, the algorithm starts doing very poorly.
But I mean, it still doesn't solve the problem when you can actually serve the load. So let's say that a Sparrow node, like it needs to serve 10 tasks, right, 10 slots, but it only asks 4 servers. So and the total like cluster capacity is 100. So you could serve the request, you just couldn't serve it because you hit that very specific Sparrow randomization. And so like, and then you can't hit over 50% because then your latency of your scheduler essentially goes up, right? Like
so in randomized algorithms, bad luck doesn't really happen. Yeah. That's just you just have to accept that bad luck isn't a problem. And like what it really comes down to is the idea is that what is bad luck? It's like you're flipping a coin, and every time you flip, you get tails. And so to do what you're saying, you'd have to flip thousands of coins and get a streak of thousands of tails in a row. And what you can do, and I'm just gonna hand wave through this. So what you can do is actually you can calculate like based on the rate of requests and the odds of you getting it wrong. Is that actually the universe or the Earth is going to get swallowed by the sun before it doesn't? Probably before you like get bad luck. That works. If you want to when we're like in small groups, I can like actually prove that, but I have to. Yeah, it's not super. The proof is not interesting. Well, not super interesting.
Is the Sparrow machine is a CPU bound or IO bound?
The Sparrow machines?
Yeah.
I would guess they're
network bound.
Oh man, that's a great question actually. I don't know if they're CPU or IO bound. Yeah. Both the CPU and the IO problems they have are pretty small. I would guess IO bound because the CPU problem they have is like so freaking trivial that I would be like shocked if this saturated a core to like, because you're just saying choose like 10,000 out of 100,000, like that. I would guess that it's the network card is what saturates first. Yeah.
So it will not be too much writing into hard disk, or it will be dealing.
There's no disk activity, and I'm not even. There is no hard disk in any of these things. Yeah. So yeah. Cool. So I'm going to get back now to your question about what happens if you don't want it. Okay, so there's 2 possible things you could do. One of them is you get this okay, and you send them a job, but it's a special job that says, I don't care. And then you get your special result back saying like, yeah, me neither. So, what if we do that? Well, if you send this, I don't care, and then you get this result back, me neither, then you're actually going to pay you're paying like a pretty big latency cost, because now you're not just paying this little thing between the okay and the job getting back. You're paying another, idle time, which is the time that it takes to actually receive this, and decide you don't care, and then send back the I don't care. So the other thing that you can do is something called proactive cancellation. And what this means is that instead of saying, is that what you say is you say, actually, hey, like I'm not going to be here anymore. So when you're done, you have sort of, some other, I don't know, out-of-band communication mechanism saying like, never mind. Oh, this is awful. You can't read this. Yeah. So you have this nevermind RPC that lets you just say like, yeah, whatever. And there's an interesting thing about like what is the right, which is better? Is this better or is this better? And they have an interesting discussion of this. So remember, I just want to kind of remind everyone, the reason we're doing this is because the network's latency is much faster than the time it takes to solve a problem. So because that's true, this little exchange about the I don't care messages, that should be really cheap. Proactive cancellation helps as the network becomes slower or the jobs become faster. So we're going in the direction that makes this less useful. Proactive cancellation helps to mitigate the penalty of those I don't care, those no-op jobs. So it really depends on the exact workload you're running, which is the one you want. Yeah.
So what's the additional cost of that? It doesn't seem like much because you still have to send the I don't care back.
For the proactive cancellation? So the idea is that you might still be in the middle of the queue, right? So now this machine
So
still
now
has to
it
set
has to
idle for
remove
this
you.
period, but you get to skip this idle period.
Right.
Yeah, so that's all you're doing. But like, so if your network takes 10 milliseconds to make a network call, and your jobs take 15 milliseconds, you just saved like 20%.
Right. Well, so basically, it sounds like you're moving the I don't care message earlier in time. Right?
Exactly.
So, what is there an additional cost to that? Because it seems like you may as well just do it.
Yeah. Let's see. I think that they actually have a reason maybe that it doesn't work. Yeah. No, I don't think it really. Yeah, I think it's probably better just to always proactively cancel. There is code complexity there, though, that for some problems it just doesn't matter. Yeah.
Is there an assumption that forwarding this to a friend would be negligibly faster than just flipping to the next reservation in the work queue? So like the Sparrow node has just gotten a handle for a worker that can do something. Why, if it doesn't care, why doesn't it just hand it over to one of its neighbors and that neighbor process it, as opposed to saying, I don't care, and then that time existing, and then the worker having to contact someone else? You eliminate one of those calls by just contacting a peer.
There's a damning sentence in this paper that talks about that, where they say, we don't need to implement complex bug-ridden gossip protocols. The bug-ridden part I just added, but they call them complex.
Okay.
I think that, and this also really goes back to the cancellation thing, is that, when you're designing these high-scale distributed systems, performance is in many cases not, it might be the first goal, but it's very close second, or maybe even tied with ease of implementation. Like, when you're building these like crazy complex things, the last thing you want to do is make it so that you're the only person on the planet who understands it. You want to make it so that anybody can pick up a paper and be like, okay, yeah, I sort of see where you're going there. Like, yeah, there's no gossip handshaking, no like crazy timeout systems. So I mean, I think that it's really a lot of what Sparrow's design comes down to is like, how do we strip away everything, to result in this like really simple to implement thing. So yeah. So, any other questions about these things? So will the people that I elected to be group leaders, or people who want to be group leaders now, raise their hands? All right.
Oh, nice.
So we got 6 group leaders. Okay. So if each group leader can walk away from each other, and then people can walk towards group leaders, then I want to try to make it for like 10 minutes. We'll just sort of talk in a smaller group about it. Cool. So all right. So hopefully everyone had a chance to discuss some stuff. I definitely heard some interesting things. So like, if you guys have things that came up in your group and you want to share them, I'll go first. So one thing I learned was that actually that as an example of other places where this kind of randomized sampling is used to improve scheduling, actually like Oracle and SQL Server use them as part of their query planners. So they use that sort of, they sample the tables and they see are they sparse or dense, they decide what types of joins to use in real time. So that's just an example of the randomized sampling being applied in some other scheduling problems. I don't know if do other people have things they wanted to thought were interesting that came up, or yeah.
I have a question that we didn't totally answer in my group, and that was I was just kind of wondering like on what scale is this useful? How many worker servers do you need to have before it pays off to do this?
Sure. So so in the paper what they talk about is that they made Sparrow because they wanted to answer so many requests that a single server couldn't schedule them. And so they had something where it's like thousands of workers and hundreds or thousands of requests per second. So at 2 Sigma, we're hiring on my team. We do a lot of cool stuff with distributed systems. One of the things is we have a scheduling problem where we actually have 2 scheduling problems where we're using Sparrow. And I'll briefly remark on one of them without divulging too many secrets. So the problem that we have is similar in that we have workers. We have problems that are small, code which is big, but we want to pre-distribute. We don't know how long it's going to take. In our case, where one of the ways that we have 100 worker nodes, and maybe we actually have like 100 worker nodes and maybe 10,000 clients. It's a very different distribution. And for us, the reason that we're interested in this is that it allows us to avoid having central queues. So instead of building a central queuing system, we are sort of just smearing the queues across the rest of the cluster, which means that we don't need to worry about any of the operational overheads of doing that. And we still get sort of optimal and expectation schedules coming out of it. So I think that depending on the types of problems that you have, you can leverage these same techniques on really small clusters and still see benefits. Especially if the problem that you have doesn't fit. Like if our problem, we could solve it with Hadoop, we probably would not have done Sparrow. But given that our problem was really weird and it needed something custom, Sparrow was the easiest custom algorithm to implement with a lot of nice properties.
So you're implementing the queues on your worker just in memory or using some queuing system? No queuing system, it's all just in memory with your own code. Is that right? You can't say that.
I'm not going to say.
Redacted.
Other questions, comments, interesting things that came up?
Do we have prioritization, which I was asking you?
Yes, so right. So speaking of prioritization, essentially the way that prioritization works is, in these models, I sort of said each worker has one queue. What we can do instead is give each worker a bunch of queues. And then the worker itself can decide which queue it's going to be reading off of. So maybe the worker has 3 queues, like low, medium, and high priority. And it always deals with high priority requests before the medium, before the low. And then now you have priority. Or maybe instead you want to do fair sharing. So then each user gets their own queue, and the worker just does like round robin off of those queues. Or there's more sophisticated weighted fair sharing on multiple queues problems. So yeah, you can get both of those. And so really, that turns out to be sort of the only type of prioritization scheme that you can do with Sparrow, is something that you can represent with a set of queues and some kind of local decision. What it turns out, though, is that when you run this in practice, this actually works really well. And you can see that they get a near perfect weighted fair sharing as they dynamically adjust the two users on a cluster. And you sort of see that. And there's some diagrams in the paper that show that. On the prioritization front, though, it's not quite as bright. It turns out that because you can't cancel a task when it starts running, at least in the algorithm presented in the paper, what that means is that if a low priority task starts running and it takes hundreds of milliseconds, and say like 3 milliseconds after it starts, a high priority task comes in, it has to sit in line behind that low priority task. You can't like kill it and cause, shuffle the order. So, I mean, that doesn't seem like a tough thing to add to Sparrow, and if you did, then you would probably be able to really get better prioritization and less kind of slop as you increase load. Other questions, comments, concerns? Yes?
Other than yours, what good examples of Sparrow in the wild do you know of?
So Sparrow was written for Spark. Okay. So Spark is this like in-memory MapReduce Hadoop sort of thing, and they wrote Sparrow for Spark. That's what this paper is all about, the Spark Sparrow. I know, my implementation is the only other one that I know of. Although, I would highly recommend it. Like if you know Go, Clojure, Erlang, Scala, like all these languages, basically any language that has the primitive where here's a few channels, tell me which one gave me the answer first. If your language has that, you can probably implement this in a day. Or you can implement parts of this in a day. The batch stuff is kind of tricky. The empirical stuff's really easy. You can, the queuing stuff is medium. And it's kind of cool because like, based on the problem you're interested in or like what part appeals to you, you can just sort of choose like, yeah, I think I'm going to do power of 2 sampling with prioritization, but I don't really care about batching. I don't care about the empirical stuff. Or maybe like, I only want to do empirical stuff with power of 2, and I'm not going to worry about queues, or so it's kind of flexible in that sense. Yeah.
So yeah, actually this paper is a number of different techniques that all together like minimize response times, like clients, like workers. And what I wanted to ask is like, so maybe something in the wild would be cool, but also like some additions, like paper point system that'd be really cool to just like tweak and play with it.
Yeah, definitely.
If there are any.
There's some stuff in here, particularly at the end. Yeah, there's a thank you to, where was it? It was Samir Agarwal actually helped to run the simulations. So I believe he's at MIT. And generally anybody in academia, it's really easy to find their email address because it's all over their papers. So you can find him or any of the paper's authors. And like 70% chance they'll give you their simulation, 30% chance they're saving it for their next publication. But you know, yeah, I mean, they had a simulator. Huh? Yeah, right, yeah. You just probe them all, see who responds first, you know, go from there. So, but they definitely have a simulator because they have synthetic results for like 100,000 machine clusters. They only tested it in practice in like 1,000 clusters.
Okay.
So yeah. Yes?
So I would just say anybody who's interested in real-world load balancing stuff and hasn't already read it should Google Heroku RapGenius and read about that story. It was sort of a well-documented snafu.
Yeah.
Interesting read.
So the Heroku RapGenius thing, once you read about that, what you should think to yourself is, Power of 2 scheduling would have solved all their problems.
Rededicate servers.
Huh?
Or like rededicate servers for all the crazy amount of money you spend.
Yeah, I mean, or just, I don't know. There's lots of things. I'm going to go with Power 2 scheduling would have solved all their problems. So, yeah. Any other comments? Cool. Well, thanks all for coming.